after all the work we've been doing with fluids, you probably have a pretty good sense of what pressure is. But now let's think a little bit about what it really means, especially when we think about it in terms of a gas in a volume. And remember, what was the difference between a gas and a liquid? They're both fluids. They both take the shape of their containers, but a gas is compressible while a liquid is incompressible. So let's start focusing on gases. So let's say I have a container. Say, let me draw a cube. This is my container. And I have a bunch of gas in it. And so what is a gas made of? Well, it's just made up of a bunch of the molecules of the gas itself. And I'll draw each of the molecules by a little dot. So it's just going to have a bunch of molecules in it. Right? Many, many, many more than what I've drawn, but that's indicative. And they'll all be going in random directions. Let me draw their this one might be going really fast in that direction. That one might be going a little bit slower in that direction. They all have their own little velocity vectors, and they're always constantly bumping into each other and bumping into the sides of the container and ricocheting here and there and changing velocity. But in general, especially at this level of physics, we assume that these are ideal, that this is an ideal gas, that all of the bumps that occur, there's no loss of energy, or essentially that they're all elastic bumps between the different molecules. So there's no loss of momentum. So let's keep that in mind, and everything you're going to see in high school and on the AP test are going to deal with ideal gases. So let's think about what an ideal gas, what pressure means in this context. So a lot of what we think about pressure is something pushing on an area. Well, if we think about pressure here, let's pick an arbitrary area. Let's take this side. Let's take this surface of its container. What is the pressure? Where is the pressure going to be generated onto this surface? Well, it's going to be generated by just the millions and billions and trillions of little bumps every time. Let me draw a side view. So if this is the side view of the container, of that same side, every second, so there's always these little these molecules of gas moving around, and if we pick an arbitrary period of time, they're always ricocheting off of the side. This one might, let's say, we're looking at time over a super small fraction of time. Over that period of time, this one might end up here. This one maybe bumped into it right after it ricocheted, came here. This one changes momentum, goes like that. This one might already have been going in that direction. That one might ricochet. But what's happening is, in any given moment, since there are so many gases, so many molecules, that there's always going to be some molecules that are bumping into the side of the wall. And when they bump, they have a change in momentum, right? And all force is change in momentum over time. Change in momentum over some change in time, right? And what I'm saying is that in any interval of time, over any period, any change in time, there's just going to be a bunch of particles that are changing their momentum on the side of the wall. And so that is going to generate force. And so if we think about how many on average, because it's hard to keep track of each particle individually, when we did kinematics and stuff, we would keep track of the individual object at play. But when we're dealing with gases and kind of the things on a macro level, you can't keep track of any individual one unless you have some kind of unbelievable supercomputer. But we can say on average, this many particles are changing momentum on this wall in this amount of time, and so the force exerted on this wall or this surface is going to be whatever, x. And then if we know what that force is and we know the area of the wall, we could figure out pressure, right? Because pressure is equal to force divided by area. So what does this help us with? Well, I wanted to give you that intuition first, and now I'm just going to give you really the two things. Actually, I'm going to give you the one formula that you really just need to know in thermodynamics, and then as we go into the next few videos, you'll hopefully get I'll kind of prove to you why it works and hopefully give you more of an intuition. So now you understand, hopefully, what pressure means in the context of a gas in a container. So with that out of the way, let me give you a formula, and I hope by the end of this video you have the intuition for why this formula works. So in general, if I have an ideal gas in a container, the pressure exerted on the gas, on the side of the container, or actually even at any point within the gas, because it'll all become homogeneous at some point, and we'll talk about entropy in future videos. But the pressure in the container and on its surface times the volume of the container is equal to some constant. And we'll see in future videos that that constant is actually proportional to the average kinetic energy of the molecules bouncing around. And that should make sense to you, right? If the molecules were moving around a lot faster, then you would have more kinetic energy, and then they would be changing momentum on the sides of the surface a lot more, so you would have more pressure. But let's see if we can get a little bit more intuition onto why pressure times volume is a constant. So let's take one example. Let me take, oh, that's not what I wanted to do. I'll do a different color. So let's say I have a container now, and it's got a bunch of molecules of gas in it. And just like I showed you in that last right before I erased, these are bouncing off of the sides at a certain rate, right? They all have the same, all of these molecules on average, each of the molecules might have a different kinetic energy. It's always changing because they're always transferring momentum to each other. But on average, they all have a given kinetic energy, right? And they keep bumping at a certain rate into the wall, and that kind of determines the pressure. Now, what happens if, I don't know, I were able to squeeze the box? So if I were able to decrease the volume of the box. So let's say this is, I just take that same box with the same number of molecules in it, but I make the volume of the box smaller. What's going to happen? Well, I have the same number of molecules in there. I have the very same number of molecules in there. And they have the same kinetic energy. And so on average, they're moving with the same velocities. So now what's going to happen? They're going to be hitting the sides more often, right? At the same time here that, say, this particle went bam, bam, now it could go bam, bam, I don't know, bam. They're going to be hitting the sides more often. So you're going to have more changes in momentum. So you're actually going to have, each particle is actually going to exert more force on each surface, because it's going to be hitting them more often in a given amount of time. And the surfaces themselves are smaller. So you have more force on a surface and on a smaller surface, so you're going to have higher pressure. So hopefully that gives you an intuition that if I had some amount of pressure in this situation, if I squeeze the volume, the pressure increases. And another intuition, if I have a balloon, right? What blows up a balloon? Well, it's the internal air pressure of the helium or your own exhales that you put into the balloon. And the more and more you try to squeeze a balloon, let's say if you squeeze it from all directions, it gets harder and harder to do it, right? And that's because the pressure within the balloon increases as you decrease the volume. So if volume goes down, pressure goes up, right? And that makes sense. That follows, when they multiply each other, you have to have a constant. And so let's take the same example again. And what happens if you make the volume bigger? So let's say I have, now that's, huge like that. I should have done it more proportionally, but I think you get the idea. I have the same number of particles. And so say I had a particle here, and in some period of time, it could have gone bam, 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 right? It could have hit the walls twice or whatever. And now, in this situation, with larger walls, it might just go bam, and in that same amount of time, it'll maybe get here. It won't even hit the other wall. So the particles, on average, are going to be colliding with the wall less often, and the walls are going to have a larger area as well. So in this case, when our volume goes up, the average pressure, or the pressure in the container, goes down. Hopefully that gives you a little of intuition, and so you'll never forget this, that pressure times volume is constant. And then we can use that to do some pretty common problems, which I'll do in the next video because I'm about to run out of time. See you soon.